right, let's finish our year in chemistry. So we're going to talk a little bit about acids and bases. Acids, best definition that will take you very far is if you just remember that an acid is an H plus. An acid has hydrogen acting like a metal in a compound. That's great work. H plus is released by acids. Bases, he said, were OH minus in water. Again, you know me, I'm not going to ask you what was Arrhenius' theory. It's just a really good place to start this. Okay, sometimes I'll call H plus a proton because if you think about what hydrogen is just a proton and an electron. If you don't have an electron, it's H plus, and if you don't have an electron, all that's left is a proton. Okay, so the key here is that an acid and a base will come together and form water. And that's a fun thing to remember. There's a lot of things we'll use for that. The spectator ion. So in this case here, where the sodium and the chloride really aren't doing much, we call those spectator ions. They're not involved in this H plus OH minus coming together for water. They still sit around and float around. So we call them spectator ions. All right. So we've talked about acids. Acids have a leading H. Their typical formula is H with some anion after it. The anion's charge dictates how many hydrogens you need. So hydrochloric acid, because Cl is -1, only needs one H, whereas SO4 has a -2 charge, so you need two H's for H2SO4. PO4 has a -3 charge, so you need H3PO4. Weak acids, acetic acid, citric acid, things you can eat, right? Ascorbic acid, vitamin C, those are all weak acids. Bases typically have a metal with OH, and again, it's the metal's charge that'll determine how many OH minuses you need. So sodium has a +1 charge, so it needs one OH. Calcium has a +2 charge, so it needs its two OHs. The weak bases are amines. So nitrogen with something connected to it 3 times will tend to be your weak base. Ammonia, as an example, triethylamine, ammonium hydroxide, anything with a nitrogen on it is considered a weak base, and we'll get into that a little bit more. So out of the gate then, can you identify which of these is an acid and which of these is a base? This does not have a leading H, so that would be a base. It has that OH minus, right? This has a leading H, so that's an acid. This has a nitrogen, so that's going to be a base, weak base. This has a nitrogen, that's going to be a weak base. And this has hydroxide, so that's going to be a base. That's actually a strong base. Hydroxide again, so that's a base. Leading H, that's an acid. Leading H, that's an acid. All right, so we've done this before. Nitrogen, so that's a base. And hydrogen as a leading H, that's an acid. All right, so that we've done already, hopefully you know. So the thing you need to understand between a weak acid and a strong acid all has to do with equilibrium. Now, we haven't discussed equilibrium, so I'm going to throw it in here. Think about school. During the school day, let's think about a little school, not like Wake Tech. You have a whole bunch of kids after school starts. A whole bunch of kids are in the school, and a whole bunch of people. Occasionally, there are some people who are outside the school, and the people who are outside the school, they had appointments, or they woke up late, or they didn't have a ride, or they missed the bus, or whatever. But so during the day, the equilibrium of school, and this shouldn't be confused with thermal equilibrium, where things are all the same temperature. Equilibrium in a chemistry sense, chemical equilibrium, has to do with the fact that the process of forward and in reverse is happening at the same time. So the process of people going into the school, what happened there? There we go. Process of people going into the school and the people leaving the school is about the same. So one person goes in because they were late, but then another person leaves for a dentist appointment, right? One person goes in because they, whatever, and then another person leaves. So the processes are equal. So we stay at this ratio, basically, where we have like 95% of people in the school and 5% of people are outside the school. That ratio stays the same, even though, right, there's still some movement back and forth. So that's during school. And then we can change the equilibrium by having some shock to the system. And the shock to the system is the bell at the end of the day, right? At the end of the day, now what happens? All these kids start leaving and a few will stay behind, right? There'll be some sports and some staying late for tutoring and some whose parents will have them in an after school program, right? So there's some ratio. Now the ratio changed, but again, the ratio is going to stay the same. So maybe 15% stayed in the school and now 85% are out. And occasionally a kid might come back because he forgot his book, or another kid will leave, but that equilibrium will stay. So another way to think about it is this cat. If the cat is asleep or awake, and if you just walked through your house and gave a hash mark every time you saw the cat, whether he was asleep or awake, and at some point you would realize that he's maybe asleep more than he's awake. So it's not necessarily equal. It just means that the two states, the starting reactants and the products, are in a ratio of where they've kind of settled in. So the reaction reaches chemical equilibrium when the amounts of reactants and products stay consistent with time. And that doesn't necessarily mean they're equal. Equilibrium does not mean that it's 50-50. It's not necessarily 50-50. It's just the ratio gets established and it stays that way. All right. Why is that important? Because that's the difference between a weak and a strong acid. A strong acid is a one-way reaction. Everything kind of goes here. Okay, it's like 100% here and 0% there. There is no real equilibrium. Whereas in a weak acid, there's some back and forth, maybe 50%, or let's say, 45% of the time it's like this, and then 55% of the time the H is released. So that's what makes a weak acid an acid. Weak. So here I said 50-50, but you get the point. There's not an absolute driving toward one side or the other. Okay. So when you think about it, then, if we think of that H plus as the thing that does danger, or the thing that causes acids to be acids, a weak acid has that H plus, right? So here's this dog. That's the H plus. It's on a leash. So it's not out there doing all the damage it can do. Whereas a strong acid, that H plus is out. It's off the leash. It can do the damage it needs to do. So that's the difference between a weak and a strong acid. So let's take a look at some pictures here. This is a weak acid. You can see the HA has that hydrogen stuck to it. And a lot of the things here are that HA. In fact, I filled some in here, which have the red stuck to the blue still. And I just showed you, right? So if the red is still stuck to the anion, it's not doing the damage. It can't be that acid. And because that anion likes to hold on to that H plus on its leash, it doesn't have the pH effect that a strong acid would. Okay, whereas a strong acid, you'll see there is none of this. There's none of this HA in there. It's all gone to H plus, and that H plus is out there doing damage. Now this says H3O. We're going to get into that in a minute here, but you see how none of the H plus is connected on the leash anymore. It's off the leash. It's out there and it's doing damage. So that's the difference between a weak acid and a strong acid. The equilibrium is favoring neither side. Basically, it's more like a 50-50 mixture, whereas here there's one-way equilibrium. It's all going to the H plus. There is none of that HA. There is no dog on the leash. The H plus is out there doing damage. Okay, so that brings up Bronsted Lowry. Bronsted Lowry said that an acid is a proton donor. So anything that has the H plus that it can kick off, and a base is a proton acceptor. So anything that an H plus can land on is considered a base. So this is expanded beyond, right? So he no longer has just OH minus. So it's beyond OH minus. It includes nitrogen as a base because it accepts that proton on that lone pair. So basically what you see here, the reason why that H plus is H3O is people have philosophized basically, and it's not wrong, that H plus is such a powerfully charged particle that it wouldn't exist by itself, especially if you had water. So if you had water floating around, that supercharged H plus would basically conglomerate onto one of these lone pairs of water and exist as H3O plus. So it's a little bit of semantics. It's a little bit of philosophy. Basically, it's the same thing. H plus is out there doing damage, but because H plus is such a powerfully charged particle, it wouldn't exist on its own. It would glom on to some negative charge. And in this case, since you're full of water, it would be with the water. Okay. So let's talk about, we've talked about how constants can be limiting. I'm pretty sure we did this already. So this was originally thought of about pH. And if the Easter egg thing there can only hold a certain number of yellow and a certain number of white, right? Anytime I want to put more yellow in, I got to pull some white out. So as this goes down, right, this is decreasing, then this has to be increasing to make up for the space that M&Ms that are getting lost by the decreasing. So as one goes down, as my number of white M&Ms goes down, my number of yellow M&Ms can go up, right? We've talked about this already. That's called an inverse proportional relationship. As one goes down, the other one increases. And turns out water has an equilibrium constant. The concentration of H plus always, when multiplied by the concentration of OH minus, equals 10 to the minus 14. That's always the case. This is always the case in any solution. And because of that, there's an equilibrium constant, that 10 to the minus 14. And that constant is limiting. It means that as one of these things goes up, the other one has to go down. So just remember math with tens, right? 10 to the fifth would have 5 zeros. 10 to the minus 14, you move that decimal place, right? 14 places this way. So it's 1 over 10 to the 14th. If you multiply 10 to the 5th times 10 to the 4th, you add up your exponents, right? We did this at the beginning of the year. 10 to the minus 6 times 10 to the minus 7. You still add your exponents, even though they're negative. You combine the negatives to get a negative 13. 10 to the 8th times 10 to the minus 3. Now you can subtract because one's negative and one's positive. So that's 10 to the 5th. 10 to the 6th times 10 squared would be therefore 10 to the 8th, right? Because you're just adding them. And 10 to the minus 3 times 10 to the minus 11 would be 10 to the minus 14. You just combine the exponents when we do this. All right. So concentration table. If all of these things have to equal 10 to the minus 14, then if one is 10 to the minus 1, the other one has to equal 10 to the minus 3. If one is 10 to the minus 2, the other one has to equal 10 to the minus 12, right? These have to always equal 10 to the minus 14. That's the rule of nature. So as the hydrogen goes down, as you see here, right? The hydrogen's going down, the hydroxide has to go up. Now the problem is down here, because we're in such small numbers, you can't really see what's happening down there because it's so close to the zero, right? We would have to blow that up and blow that up to start seeing that curve like that. So that's why we have the log function. The log function helps us bring this U shape into something a little less, a little more like what we were seeing before. So there's a button on your calculator. It says log. This is the unit when we use it. You need to embrace the log. What log basically tells you is, what did I have to raise? What number did I have to raise the 10 to? What power did I have to raise 10 to equal the number here? So 10 to the minus 5 is this, right? And so the question is, if I take the log of that, it's like, what number did I have to raise 10 to equal this? And that's 10 to the minus 5. So the answer is minus 5. So log 10 to the 43rd, basically whatever it is that the power is what the log 10 to that power is. So log 10 to the smiley face would equal the smiley face. All right. So people don't like negative numbers. So pH, if you look here, all these are numbers, right? These are all negative numbers. So if we just took the log of all these numbers, we would have negative numbers. And people don't like negative numbers. It makes them uncomfortable. So we define pH as the negative log of the concentration of H plus. So 10 to the minus 6, we just said the log of that would be minus 6. And then pH is defined as the negative 6, which makes it positive. Basically, take the log of your concentration of H plus, make it positive. That's what it is. All right. So let's do some things here. The 0.1 is 1 times 10 to the minus 1. If I take the log of that, it would just be the power of 10, right? Minus 1. And if I want that negative, I want that to be plus 1, right? Negative 1 is plus 1, so the pH would be 1. The power here is negative 3, so the log of that is negative 3. And if I want a negative 3, that becomes positive 3, right? So that becomes positive 3, so the pH would be 3. This would be positive 5. pH of 5. This would be positive 7, pH of 7, positive 10, pH of 10, positive 14, pH of 14. All right. So why did we do all that? Because now our U, which has all these weird concentrations, becomes watch, right? Because all these, this 1 becomes, -1 becomes 1, this -2 becomes 2, because it's times 10 to that. This 13 becomes positive 13, and you get this. Look at that. And now everything equals 14. Nice and nice, right? So now it looks more like our egg thing. So at the end of the day, what does all this mean? If you have a pH between 1 and 6, so a pH between 1 and 6, let me turn this red. So if your pH is between 1 and 6, then that means your concentrations are higher than your OH concentrations, right? So look here, your concentrations of your acids. The number 10 to the minus 1 is bigger than 10 to the minus 13. The number 10 to the minus 5 is bigger than 10 to the minus 9. The number 10 to the minus 6 is bigger than 10 to the minus 8. So in all these situations, oops, you have an acid, which I should do in red, right? Because there's more of this and less OH. Whereas down here, the opposite is true. Your base is larger than your acid, right? So this is base, because now your OH minus has the bigger number than your H plus. So in pHs of 1 to 6, that's an acid. Okay, that's acid. And in pHs of 8 to 14, what that means is your base has now more. So we call those base. And when they're equal, we say they're neutral. All right, so let's do some of these problems. If I give you the pH, what that's basically asking then, to find the concentration of H plus. Remember, we said that the log of the concentration of H plus, right, made positive will equal the pH. So basically what we need to do then is raise everything to the power of 10. So 10 to the power of the negative pH will give you the concentration of H plus. That's how that's going to work. So if I tell you the pH is 9.15, we're going to take 10, raise it to the power of 9.15, and that'll give us the concentration of H plus. So if we do that on a calculator real quick, what we get is, right, so 9.15, we want to make that negative, so we want to use this plus minus thing. We don't want to use the addition subtraction buttons because that's going to try to do a function. We just want to make this negative and raise 10 to that power, and we get 7.08 times 10 to the minus 10. Would you agree with that? 7.08 times 10 to the minus 10. So the answer is 7.08 times 10 to the minus 10. All right, that equals our concentration of H plus. So let's do the next problem. So the next problem, right, so this equals concentration of H plus. All right, the next problem now is going the other, no, it's not going the other way. This one is going to use the formula that the concentration of H plus times the concentration of OH minus always equals that constant, right? This is a natural phenomenon that always equals 10 to the minus 14. So I've given you the concentration of H plus. So this is given. So we have 3.4 times 10 to the minus 8, and we don't have the concentration of OH minus. And we're going to try to find it as equal to 10 to the minus 14. So again, let's look at how we would do this on our calculator. So we're going to take a couple things we could do. We could either do 1 exponent negative 14, right? That's 10 to the minus 14. Or if you have this button, you can put 14, make it negative, and raise that to the power of 10. And we're going to divide that by 3.4 times 10 to the minus 8. So exponent negative 8. And bam. And that gives us 2.94 times 10 to the minus 7. So let's look at what that did here. What we did is we divided both sides by 3.4. times 10 to the minus 8, right? And so the concentration of OH minus equaled whatever I just had written there, which I believe was 2.94 times 10 to the minus 7. Maybe I'm remembering, and that's the concentration. So that's molarity. All right. Then the last one is probably the easiest one. If I'm asking you for the pH and I give you the concentration of H plus, you're just going to take that concentration of H plus and hit the log button. So we need the log of that. And then we want to make sure we make it positive. So let's take a look at that, how you do that. We're just going to take 5.2 times 10 to the minus 3. So 5.2 exponent negative 3. And hit the log button. Bam. So the answer is, make sure this is positive, positive 2.28. Right? So that would be positive 2.28. Okay? So notice it's in the ballpark of what your exponent is when you do that, but it's not exactly. Okay. Real quick, acid-base titration is something you're going to do moving forward. It's when you take the acid and the base and you mix them together to make sure they're neutral, that they turn into water. I did a video where I do one of these. You can watch it if you want. This is not going to be on your final. This is not going to be, it's just something for you to know that titration means the moles of H plus equals the moles of OH minus. We call that the equivalence point. So basically, you have a whole bunch of acid. Let's say this is a bunch of, right? You have a whole bunch of H pluses and you're shooting OH minus at it. So every time you hit one of these H pluses, you turn it into water. And when you turn it into water, that basically means you have a whole lot of H pluses left behind, right? And at some point, you will turn all these H pluses into water and everything will be water and your pH will be 7. So when you do something like this, don't worry about that. You start with a bunch of acid, right? So here's your acid. And then as you keep shooting OH minus at it, so you're adding base. And like I said, just watch me do one of these. So I'm shooting OH minuses at that. And at some point, we reach the equivalence point, which is where all the H plus and OH minus turned into water. All of it's turned into water. So all of my H pluses are gone. All my OH minuses turned them into water. And there's nothing left but water. And that's the point of a titration. That's all you need to know. Okay. So Bronsted Lowry, this you do need to know again. He said the proton donor and the proton acceptor. So when you do Bronsted Lowry stuff, you have to establish sort of this idea of a conjugate pair. So water, right? So water in this situation was the acid. It gave its H plus to NH3. Okay, that turned NH3 into NH4 and it turned water into OH minus. So we say that water and the OH minus are a conjugate pair because they're related by the difference of an H plus. Okay, so water, by losing its H plus, became OH minus, and now look, now it's a base. Because it lost its H plus, it can take one back, and that makes it a base. So that's the conjugate base is what we call that. And NH3, by gaining that H plus, became an acid. So now it has the H plus, so that became a conjugate acid. So we call those conjugate pairs. Here is another way to look at it. It's playing tag. Basically, these things are playing tag, and H plus is sort of like the sticker that you have to put on someone to make them it. So here's water, right? This was the acid. It has this H plus. Here's ammonia, NH3. And what happens is that water gave ammonia that H plus. And when it gave it that H plus, now it turned this into it. This is it, right? This is the acid. And now it's the base. And so now this can go tag that with its H plus and go back. So that's sort of what this is. And obviously you can see here that's an equilibrium. So they go back and forth. So the acid gives its H plus, makes the other thing it. And by being it, it's an acid now. And it has an H plus to give up. All right. So in this situation, who gave up the H plus and who? Well, we already did that one. Okay. So there. Okay. So there's a couple examples of that on the thing, trying to establish who the acid and the conjugate acid and the base and the conjugate base are. Just remember the acid is related to the conjugate base and the base is related to the conjugate acid, right? They're picking up that H plus. Okay. So buffers. What a buffer does, the reason why your blood doesn't become very acidic when you have stomach acid in your stomach, right? Is because what blood has in it is called a buffer. And the buffer basically will turn anything that's strong into something weak. So think about having a strong acid added to where there's a weak acid. So a weak acid has this ability to hold hydrogen onto the H plus onto the leash. So when we have a buffer, what we have is basically a weak acid and a weak base. We have a weak acid, and we also have in a buffer a weak base. And the beautiful thing about that is when you add a strong acid to a weak base, what happens next? The strong acid, by definition, has the dog off the leash and wants to give that H plus to the weak base. That turns the weak base into a weak acid. All right, so let's look here. If this strong acid had with it here, I'll make the buffer purple. So here's a weak base. So this is some minus thing. So let's say that's like C2H3O2 minus 1. All right, that's a weak base. It will then take that hydrogen from that strong acid, and now it's become, that wasn't supposed to be yellow, that was supposed to be red. There we go. And now it's become a weak acid. So if you add an H to this, now it's acetic acid. So it turned a strong acid into a weak acid by being there. And likewise, if you add a weak base to something that has a weak acid, so one of these right here, that's a weak acid, right? What a weak base is going to do, like what a strong base would do, if we add a strong base, so like OH minus, is like, hey, I want to cause some trouble. What will happen is that weak acid will give up its H plus. So it'll be like, oh wait, you're a strong base, here, take my H plus, and I'll give that H plus, make that into water, and what'll be left behind now is this weak base, this acetate anion, which will then not be as severe a pH issue as OH minus. That's the best I can do. I wish I could do more of this, but again, that's just an introduction in case you ever wonder why blood doesn't change its pH. It's because there exists in blood what the actual acid and base are is H2CO3. That's the weak acid, and then CO2. CO2 is the weak base? Anyway, I'm thinking it's basically there's in it, and that becomes water and CO2. And if you add base, you make more CO2. And if you add acid, you make more H2CO3. All right. Last thing, Lewis acid. Lewis basically said, why is Bronsted only making it H plus? What, if anything, sort of occupies the lone pair? So nitrogen, according to Bronsted, you had to have an H plus hang out by that lone pair to be an acid. And so what Lewis said is, why does it have to be an H plus? What, if anything, takes over the lone pair of another atom and sort of gloms on, right? So why is it that the freeloader has to be hydrogen? What Lewis basically said is, why can't the freeloader be anything? Anything that's a freeloader, so here's my freeloader, can be an acid. So boron can only make 3 bonds. It may want 4 just to be sort of like, feel like it's a noble gas too. I mean, yeah. So if it freeloads on a nitrogen, why isn't that basically acting like an acid? Okay. And in future classes, you'll talk about amino acids. They have the acid group and a basic group. So they're mostly neutral. Sometimes they have 2 basic groups, which makes them basic. Sometimes they have 2 acid groups, which makes them acidic. So the acid group is a COOH and the base group is the nitrogen. All right. That's all I can tell you.